Hi, I'm Rachel. This is a presentation on hydrogen. There are 9 learning objectives.
Number 1. To present informed opinions on the position of hydrogen in the periodic table. Number 2. To identify the modes of occurrence and preparation of dihydrogen on a small and commercial scale. Explain how different elements combine with hydrogen to form ionic, molecular and non-stoichiometric compounds. Describe how an understanding of its properties can lead to the production of useful substances and new technologies. 5. Understand the structure of water and use the knowledge for explaining physical and chemical properties. 6. Explain how environmental water quality depends on a variety of dissolved substances. 7. Acquire the knowledge about heavy water and its importance. 8. Understand the structure of hydrogen peroxide, learn its preparatory methods and properties. Finally, 9. Understand and use certain terms: electron deficient, electron precise, hydrogenation. Topic 1. Position of hydrogen in the periodic table.
Resemblance with alkali metals.
Electronic configuration, electropositive nature, reducing nature, combination with nonmetals to form halides, sulfides and oxides, liberation at cathode.
Resemblance with halogens.
Electronic configuration, has to gain one electron to gain octet, electronegative nature, ionization enthalpy, non-metallic character, liberation at anode. Hydrogen is less electropositive than alkali metals and less electronegative than halogens. The size of proton is much lesser than the normal range. Oxide of hydrogen is neutral, unlike alkali metals which are bases and halogens which are acids. Hence, hydrogen is unique in its behavior and cannot be placed with alkali metals or halogens. It is best placed separately in the periodic table.
Occurrence and isotopes of hydrogen.
Occurrence.
Most abundant element.
Principal element in the solar atmosphere.
Light nature.
In combined form, it constitutes 15.4% of the crust.
In animal and plant tissues, hydrides, etc.
Consistent element in Jupiter and Saturn.
Isotopes of hydrogen.
Protium, no neutrons. Deuterium, 1 neutron. Tritium, 2 neutrons. Same number of electrons, hence the chemical properties remain the same, but the rate of reactions is different due to the different enthalpy of bond dissociation.
Preparation of dihydrogen. Laboratory preparation.
Reaction of granulated zinc with dilute hydrochloric acid. Reaction of zinc with aqueous alkali.
Commercial preparation.
Electrolysis of acidified water using platinum electrodes. Electrolysing warm aqueous barium hydroxide solution between nickel electrodes, which yields a high purity. As a byproduct in the manufacture of sodium hydroxide and chlorine through the electrolysis of brine. Reaction of steam on hydrocarbons or coke at high temperatures in the presence of catalyst. The first one is a general equation and the second one is an example. The mixture of carbon monoxide and hydrogen is called water gas, and since this is used for the synthesis of many hydrocarbons, it is also called syngas. The process of producing syngas from coal is called coal gasification. The production of hydrogen can be increased by reacting carbon monoxide of syngas mixtures with steam in the presence of iron chromate.
Properties of dihydrogen.
Physical properties.
Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water.
Chemical properties.
The chemical behavior of dihydrogen is determined to a large extent by bond dissociation enthalpy. The hydrogen-hydrogen bond dissociation enthalpy is the highest for a single bond between two atoms of any element. Due to this, it is relatively inert at room temperature. Since its orbital is incomplete with 1s1 electronic configuration, it does combine with almost all the elements. It accomplishes reactions by loss of the only electron to give hydrogen positive, gain of an electron to form hydrogen negative, sharing electrons to form a single covalent bond.
Reaction with halogens.
It reacts with halogens to give hydrogen halides.
Reaction with dioxygen.
It reacts with dioxygen to form water, which is exothermic.
Reaction with dinitrogen.
It reacts with dinitrogen to form ammonia.
Reaction with metals.
It combines with many metals at high temperatures to yield the corresponding hydrides.
Reaction with metal ions and metal oxides.
It reduces some metal ions in aqueous solutions and metal oxides into corresponding metals.
Reaction with organic compounds.
It combines with many organic compounds in the presence of catalysts to give useful hydrogenated products. Hydrogenation of vegetable oils using nickel gives edible fats. Hydroformylation of oil fins yields aldehydes, which reduced later give alcohols.
Uses of dihydrogen.
It is used in the synthesis of ammonia. Dihydrogen is used in the manufacture of vanaspati fat. It is used in the manufacture of bulk organic chemicals like methanol. It is widely used for the manufacture of metal hydrides. It is used for the preparation of hydrogen chloride. It is used to reduce heavy metal oxides to metals. Atomic hydrogen atoms are allowed to combine on the surface to be welded to generate the temperature of 4000 Kelvin. It is used as a rocket fuel in space research. Dihydrogen is used in fuel cells for generating electrical energy. It does not produce any pollution and releases greater energy than other fuels.
Hydrides.
Dihydrogen, under certain reaction conditions, combines with almost all elements except noble gases to form binary compounds called hydrides. The hydrides are classified into three categories:
Ionic or saline or salt-like hydrides, covalent or molecular hydrides, metallic or non-stoichiometric hydrides.
Ionic hydrides.
These are stoichiometric compounds of dihydrogen formed with most of the S-block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as lithium hydride, beryllium hydride, and magnesium hydride. The ionic hydrides are crystalline, non-volatile, and non-conducting in solid state. Their melts conduct electricity, and the electrolysis liberate dihydrogen gas at anode, which confirms the existence of hydrogen ion. Saline hydrides react violently with water, producing dihydrogen gas. Lithium hydride is rather unreactive at moderate temperatures with oxygen or chlorine. It is therefore used in the synthesis of other useful hydrides.
Covalent hydrides.
These are molecular compounds of dihydrogen formed with most of the p-block elements.
These are of three types: electron deficient,
Electron rich.
electron precise.
Electron deficient.
Has too few electrons for writing its Lewis structure. All group 13 elements will form electron deficient compounds, act as Lewis acids, that is electron acceptors, example diborane.
Electron rich.
Has excess electrons which form lone pairs. All group 15 and 17 elements will form electron-rich compounds, act as Lewis bases, that is, electron donors. The presence of lone pairs on highly electronegative atoms like nitrogen, oxygen, and fluorine hydrides results in hydrogen bond formation. Example, ammonia, water, etc.
Electron precise.
Has enough electrons for writing its Lewis structure. All group 14 elements will form electron precise compounds. Tetrahedral geometry. Example, methane. Water.
Physical properties.
Colorless and tasteless liquid. The unusual properties of water in liquid and solid states are due to the presence of excessive hydrogen bonding. Has high freezing point, high boiling point, high heat of vaporization, high heat of fusion. Has higher specific heat, thermal conductivity, surface tension, etc. compared to other liquids. Excellent solvent for transportation of ions and molecules.
Structure of water.
In the gas phase, water is a bent molecule with a bond angle of 104.5 degrees and oxygen-hydrogen bond length of 95.7 picometer. It is a highly polar molecule. In the liquid phase, water molecules are associated together by hydrogen bonds.
Structure of ice.
Ice has a highly ordered three-dimensional hydrogen bonded structure. Each oxygen atom is surrounded tetrahedrally by four other oxygen atoms at a distance of 276 picometer. Hydrogen bonding gives ice a rather open structure with wide holes. These holes can hold some other molecules of appropriate size interstitially.
Amphoteric nature.
It has the ability to act as an acid as well as a base. Following are two examples.
Redox reaction.
Water can be reduced to dihydrogen by highly electropositive methods. Water is reduced to oxygen during photosynthesis. Water can also be reduced using fluorine.
Hydrolysis reaction.
Due to high dielectric constant, it has very strong hydrating tendency. It dissolves many ionic compounds and hydrolyzes some ionic and certain covalent compounds. Following are three examples.
Hydrates formation.
From aqueous solutions, many salts can be crystallized as hydrated salts. Such an association of water is of different types: viz., coordinated water, interstitial water, hydrogen bonded water.
Hard water.
Calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard. It does not give lather with soap. Hard water forms come with soap. Soap containing sodium stearate reacts with hard water to precipitate out calcium or magnesium stearate. Unsuitable for laundry and harmful for boilers because of the deposition of salts.
Temporary hardness.
Temporary hardness is due to the presence of calcium or magnesium carbonates. It can be removed by boiling. Two examples. During boiling, the soluble magnesium hydrogen carbonate is converted into insoluble magnesium hydroxide and calcium hydrogen carbonate is changed into insoluble calcium carbonate. It is because of the high solubility product of magnesium hydroxide as compared to that of magnesium carbonate that magnesium hydroxide is precipitated. These precipitates can be removed by filtration.
Clark's method. In this method, calculated amount of lime is added to hard water, which precipitates out calcium carbonate and magnesium hydroxide, which can be filtered out. Two examples.
Permanent hardness.
It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. It can be removed by the following methods. Treatment with washing soda. Washing soda reacts with soluble calcium and magnesium chlorides and sulfates in hard water to form insoluble carbonates. Following are two examples. Calgon's method. Reaction with sodium hexametaphosphate. Two examples.
Ion exchange method. Zeolite or permatite. Hydrated sodium aluminium silicate is zeolite. When the zeolite is added in hard water, exchange reactions take place. Zeolite is said to be exhausted when all the sodium is used up.
Nowadays, hard water is softened by using synthetic cation exchangers. Cation exchange resins contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin is changed to RNA by treating it with sodium chloride. The resin exchanges sodium positive ions with calcium and magnesium ions present in hard water to make the water soft. Here, R is the resin anion. The resin can be regenerated by adding aqueous sodium chloride solution. Pure demineralized water, free from all soluble mineral salts, is obtained by passing water successfully through a cation exchange and an anion exchange resin. In this cation exchange process, hydrogen exchanges for sodium, calcium, magnesium and other cations present in water. This process results in proton release and thus makes the water acidic. In the anion exchange process, hydroxide exchanges for anions like chlorine, hydrogen carbonate, sulfate, etc. present in water. Hydroxide ions thus liberated neutralize the hydrogen ions set free in the cation exchange. The exhaustive cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solutions respectively.
Hydrogen peroxide.
It is an important chemical used in the pollution control treatment of domestic and industrial effluents.
Preparation.
Acidifying barium peroxide and removing excess water by evaporation under reduced pressure. Peroxide sulfate obtained by electrolytic oxidation of acidified sulfate solutions at high current density on hydrolysis. Industrially, it is prepared by the auto-oxidation of two alkaline quinols. Physical properties.
Almost colorless liquid.
Miscible with water in all proportions and forms.
Melting point 272.4 Kelvin.
Boiling point 423 Kelvin.
Density 1.44 grams per centimeter cube.
1 milliliter of 30% hydrogen peroxide solution will give 100 milliliter of oxygen at STP.
Structure.
Hydrogen peroxide has a non-planar structure. The molecular dimensions in the gas phase and solid phase are shown in the below figure.
Chemical properties.
It acts as an oxidizing as well as reducing agent in both acidic and alkaline media.
Oxidizing action in acidic medium. 2 examples.
Reducing action in acidic medium. 2 examples.
Oxidizing action in basic medium. 2 examples.
Reducing action in basic medium. 2 examples.
Storage.
Hydrogen peroxide decomposes slowly on exposure to light. In the presence of metal surfaces or traces of alkali, the above reaction is catalyzed. It is therefore stored in wax-lined glass or plastic vessels in dark. Urea can be added as a stabilizer. It is kept away from dust because dust can induce explosive decomposition of the compound.
Uses.
It is used as a hair bleach, antiseptic, and as a mild disinfectant.
It is used to manufacture chemicals like sodium perborodate and percarbonate.
It is used in the synthesis of hydroquinone, tartaric acid, and certain food products and pharmaceuticals.
It is employed in the industries as bleaching agent for textiles, paper, pulp, leather, oils, fats, etc.
It is also used in environmental, green chemistry, in pollution control treatment of domestic and industrial effluents, restoration of aerobic conditions to sewage wastes, etc. Heavy water. It is extensively used as a moderator in nuclear reactors and in exchange reactions for the study of reaction mechanisms. It can be prepared by exhaustive electrolysis of water or as a byproduct in some fertilizer industries. It is used for the preparation of other deuterium compounds like the following.
Dihydrogen as a fuel.
Dihydrogen as a fuel releases large quantities of heat on combustion. Moreover, pollutants in combustion of dihydrogen are less than petrol. The only pollutants are the oxides of dinitrogen. This can be minimized by injecting a small amount of water into the cylinder to lower the temperature so that the reaction between dinitrogen and dioxygen may not take place. A cylinder of compressed dihydrogen weighs about 30 times as much as a tank of petrol, containing the same amount of energy. Also, dihydrogen gas is converted into liquid state by cooling to 20 Kelvin. In this view, hydrogen economy is an alternator. The basic principle of hydrogen economy is the transportation and storage of energy. Energy is transmitted in the form of dihydrogen. It is also used in fuel cells for generation of electric power. Hope you all enjoyed this video. Don't forget to hit like before you